In this video, we will see vector application of dot product in physics. The most practical application of dot product in physics would be the work done, which is related to force and displacement. So if F is a vector, which is represented for the force acted on an object, and D is the vector, which is the displacement, then we know that work done is F into D. So, and since work done is a scalar quantity, we would define this work done as F dot D. So, we can define it by saying if D, vector D, is the displacement vector of a particle moved from a point to another point after applying a constant force F on the particle, then the work done by the force on the particle is work done is equal to vector F dot product with vector D. So we can see that here. So we have vector F and vector D. Now we have illustrated three scenarios here. The first is the angle between F and D is acute. And in the second case, the angle is 90 degrees. And in the third case, the angle is obtuse. Now, in each of these cases, your work done will have an impact. I'll explain to you shortly here, and then we will go further down and we will have a better understanding. We know that the dot product formula F dot D is given by magnitude of F, magnitude of D into cos theta, where theta is the angle between F and D. So what we're actually doing is we are looking at the impression that the force F will make on this line, which is on the vector D. So we take this magnitude here, okay, the impression magnitude we can call it, and this can be measured using cos theta. Cos theta, if this is our theta, would be equal to adjacent side by the hypotenuse, and hypotenuse is magnitude of F here. So rearranging the formula, you can get the adjacent as magnitude of F into cos theta. Okay, so this is this length here multiplied by the magnitude of D, and hence we get this formula. So we will see that when cos theta is 90 degrees or cos 90, it will be cos 90 will be 0, so the work done will be 0. And when it is over 90 degrees theta, this will be pi minus theta. So then the cos pi minus theta would be negative cos theta. So let's look into each of the cases. We will look into the first case first. So we have the acute angle. The perfect example for this would be a father pulling a cart with a child. So he is applying a force here, which is in this angle, whereas the object is moved in this direction. And so this is our displacement vector, and this is our vector F. All right, so F and D. And the angle between the two is 30 degrees. So this is a perfect example to illustrate work done when the force and the displacement is less than 90 degrees angle. Okay, so we know that this cos theta here will be a positive value. Therefore, F dot D would be a positive value. Therefore, work done in this first case will be a positive value. Right? Then let's take a look at the second case. So in the second case, you have this man here who's carrying a briefcase. So this briefcase is carried because of the force that is being applied in this direction by this hand. Right? So there is a gravity pulling it, but this force F is keeping the briefcase from falling down. All right. Now the man is moving and the object is moving, but this force doesn't have any impact on it. Okay, so this displacement and this force, if you look at the dot product, their resultant would be 0. So that is why we call cos 90 degrees to be 0, the angle between them. So in this case, in the second case where the displacement vector and the force vector, or the vector A and vector B, when they are in a dot product, the result is a 0. So the work done in this case would be 0. Okay, now let's look at the third case. So in this case, the force is in this direction and the displacement is in this direction. So it's making a obtuse angle here. All right. So let's look at this illustration where you have a man trying to pull this bundle using a pulley. Okay. So the force is in this direction and the bundle is moving in this direction upward. So you have the displacement in this direction and the force in this direction. And the angle between them is pi minus theta. Remember, the vector angle is always measured from the outgoing side. You don't take the angle here, which is the internal side, but you take it from the external side. Look at the direction. So this would be the angle. Okay. So the force is acting in this angle and the displacement is in this direction. So our angle between the two is pi minus theta. Okay. So what happens here is, we know that cos pi minus theta is a negative value. Okay. So therefore our f dot d would be a negative value. Therefore the work done will be in negative value. All right. So let's consider two position vectors A and B. A is defined as A1 I cap plus A2 j cap plus A3 k cap, and vector B is defined as B1 I cap plus B2 j cap plus B3 k cap. So when you do the dot product of these two, your result is A1 B1 plus A2 B2 plus A3 B3. Now remember, this is a scalar quantity which will be a single value. All right. Let's look at an example. A particle acted upon by constant forces 2i cap plus 5j cap plus 6k cap and minus I cap minus 2j cap minus k cap. So we have two forces acting here. Let's call each of them as F1 vector and F2 vector. Okay. So a particle acted upon by constant forces vector F1 and vector F2 is displaced from the point 4 minus 3 minus 2 to the point 6 1 minus 3. So I can define this point as A and this point as B. Find the total work done by the forces. So we need to find W, which is the work done, and this is equal to force into displacement. So our total force, or the resultant force I can define that as F is equal to F1 plus F2, since we have two forces acting. So if I add them up, 2i cap plus 5j cap plus 6k cap plus minus I cap minus 2j cap minus k cap. So the answer would be I cap plus 3j cap plus 5k cap. So this would be my vector F. Okay, now my displacement vector D is, I can define that the object was moved from point A to B. Okay, so we have this point A and point B. And so the vector OA, which is from the origin, can be defined as, since the point is defined as 4 minus 3 and minus 2, vector OA will be 4i cap minus 3j cap minus 2 k cap, and OB will be equal to 6 I cap plus j cap minus 3 k cap. Okay. The displacement vector is, it is displaced from A to B. So this is our vector, which is A to B. So vector AB can be defined as, if this is vector OA in this direction and vector OB in this direction, AB can be defined as minus OA plus OB. Okay, because OA is in this direction. So changing the course of direction, minus OA plus OB. So in other words, vector OB minus vector OA. Right. So let's put them down. OB is 6 I cap plus j cap minus 3 k cap minus of vector 4 I cap minus 3 j cap minus 2 k cap. So that would be equal to 2 I cap plus 4 j cap minus and plus. So it will be minus k cap. Alright. So let's now find our work done. That's equal to vector F dot product with vector D. That's equal to I cap plus 3 j cap plus 5 k cap, which is our vector F. Okay. Dot product with our displacement vector 2 I cap plus 4 j cap minus k cap. So we know that you have to just multiply the coefficients of I, j and k. So our result would be 1 into 2 plus 3 into 4 plus 5 into minus 1. That would be equal to 2 plus 12 minus 5. And that's equal to 9 units. So that's our answer. Okay. In this problem, it reads a particle is acted upon by the forces 3 I cap minus 2 j cap plus 2 k cap and 2 I cap plus j cap minus k cap is displaced from the point 1 3 minus 1 to the point 4 minus 1 lambda. If the work done by the forces is 16 units. So here we are given the work done. Find the value of lambda. We need to find lambda. So this is our F1 vector, F2 vector. So the resultant force is F is equal to F1 plus F2, and that is equal to 3 I cap minus 2 j cap plus 2 k cap plus 2 I cap plus j cap minus k cap. So adding them together, we get 5 I cap minus j cap plus k cap. Alright. Similarly, if we call this point A and B, our displacement vector would be A to B, and that would be defined as OB minus OA, as we saw in the previous problem. And we can further, our OB would be 4 I cap minus j cap plus lambda k cap minus OA vector would be I cap plus 3 j cap minus k cap, and that is equal to 3 I cap minus 4 j cap plus lambda plus 1 k cap. So that's our vector D. Okay, so we are given f dot D is equal to 16. Therefore, our f dot D is 5 I cap minus j cap plus k cap dot product with 3 I cap minus 4 j cap plus lambda plus 1 k cap is equal to 16. So further simplifying this, 15, 5 3s are 15, minus 1, minus 4, plus 4, plus 1 into lambda plus 1 is equal to 16. So we can say lambda plus 20 is equal to 16. So lambda is equal to 16 minus 20. So lambda is equal to minus 4. So that's our answer. Thank you for watching Maths Tutorial Anand. Please like and you can comment if you have any questions, and do not forget to subscribe to get more videos like this.